Pop quiz today, the first problem was 1/6 perturbation theory, where the idea is that you can calculate the true partition function by getting ensemble averages in the reference partition function. And you have to correct for the fact how much did the energy change by, and the energy is actually the difference is e to the power minus beta un 1. That's the term that comes up over here. So this is an important formula. And even if you don't remember the formula, it's not hard to derive, and that's something you should be able to derive in a few seconds. It's not hard. Second one, come on, we just spoke about it. 5 of you still got it wrong. We just spoke about this, that if j is equal to -1, that means minus j equal to +1, then it would look like up, down, up, down, up, down, up, down. So that's not good. Maybe it's too early in the morning. Or maybe you are as upset as I am by Donald Trump declaring that he will be restricting immigration into the country. It could be one of those two reasons. Anyway, let's not go there. Maybe we should. I don't know. Okay. So good. So this is the simple model. And if you had an H existing in the system, that itself would dictate how the spins would be. So the point that I was trying to make is, if you have a model which looks like minus J.
My screen's frozen in the quiz.
Yeah, that happened to the poll. Sorry for that. Let me start it again. Thanks for telling me. Stop share. Share screen. Okay, now it should be visible. Okay, so we have E minus J SIFJ. And how did we introduce the H term? We had minus summation I is equal to 1 to N H mu I SI. So what you just did in the pop quiz was with H is equal to 0 and J is equal to -1. And in this case, the configuration will be up, down, up, down, up, down, or plus, minus, plus, minus. We are using these things analogously. Plus, minus, blah, blah, blah. Now you could imagine that H is 100,000 and J is equal to -1, right? So in this case, the contribution from H is much more than J. And now if H is equal to, so this thing applies here, and if H is equal to 100, or let's add one more 0, and J is equal to -1, then most of the time the configuration will look like as if all the spins are trying to point along H, and they will all look like this, right? But now you could imagine some intermediate case where H is equal to, let's say, 0.5 and J is equal to -1. Now, H wants the system to look like this, and J wants the system to look like this. So there is a competition. So in this system, you can then come up with wonderful phase diagrams where one axis is H, the other axis is J. In physical chemistry, the phase diagrams that you think of are pressure temperature phase diagram, right? Or composition temperature phase diagrams. This is a different type of phase diagram where you have external magnetic field on one side and coupling constant on the other side. It's not very different from the pressure temperature phase diagrams that you think of, right? One variable is being changed. It's in the same spirit. And here you can imagine you could draw phase boundaries. As to here, it is anti-ferromagnetic, and here it is ferromagnetic, and you can talk about where is the phase boundary going to be, this and that. And every phase diagram will depend on the form of interaction. Do you have only first number interactions? Do you have higher number interactions? So you could come up with lots and lots of wonderful things over here. What we are going to do next is to really think about the quantity called average magnetization. Average magnetization, which is denoted as bar of M or bracket of M, which is a sum of I is equal to 1 to N mu SI. This is the sum that we are interested in. So again, let's consider a model like the one you did in the pop quiz, but let's consider something for now where it looks like minus SI SJ. So here in this model, we know that at zero temperature, all spins would like to be the same sign, right? We would like to have either Si is equal to Sj is equal to +1, or we would like to have Si is equal to Sj is equal to -1 at zero temperature. But as you start to increase the temperature, there will be disorder. It's bound to happen. If temperature was infinite, expecting that all spins will still be perfectly ordered in the same direction, that's not going to happen. So if for this system, and I'm not talking about 1D or 2D specifically, I'm talking about some general Ising model. If for this system, we are interested in plotting and here let's not use this notation, let's use bracket because I will reserve the bars for modulus. Let's think that we are trying to plot the modulus, the absolute value of the magnetization as a function of temperature. So at zero temperature, it's going to be some large positive value, right? It will be mu n. Why? You can see that because all the SIs will be either +1 or -1, and you have n of them, so it will be mu n. As you increase the temperature, it will start to fall down. And at some temperature, it will go to zero. Entropy will take over, and then it will just stay like this. This temperature is called critical temperature. It's of great interest. It's especially of enormous interest as to what is the polynomial or algebraic expression for how m behaves as t approaches Tc. This is of great importance. For many systems, it happens so that these phenomena can be described by using something called critical exponents, which basically talks about what is the slope at which these things approach zero. And it just so happens that Ising models tend to have very well-defined critical exponents. Irrespective of what system you are trying to describe, they tend to have exactly the same critical exponents. So you can go and look up. There is a lot of work on this as to how these are. We will not talk about critical exponents that much, but we will, however, talk about the value of critical temperature. So the claim that I'm making today and made last time is that critical temperature is equal to zero in one dimension, in absence of external magnetic field. This is a very intriguing statement. This says that if you try to arrange a bunch of spins, either like plus, 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 or minus, 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 you can have them exist at, this will happen, and we have infinite number of spins. That's quite critical, always thermodynamic limit. We have lots and lots of spins. If you can come up with lots of funny business if you look at small number of spins. So this will happen only at absolute zero. As soon as you perturb the temperature by the slightest possible amount, a nanokelvin or a picokelvin or whatever you have, the magnetization will go to zero. You will have complete chaos. The things will be completely random, up, down, 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 whatever. And the net magnetic moment will go to zero. Any amount of perturbation is enough to cause the system to lose its order completely. And you can see why I'm excited about this, because this seems like quite a profound thing, right? You're trying to design a material in 1D, which is a conducting material. And it depends on, and let's say it is made up of certain molecules attached to each other. And electron has to pass from this molecule to this molecule to this molecule. And in order for the electrons to pass, the molecules all have to be in some on state, or in some, let's say they have to all be in an on state. The only way this conduction will happen if all the molecules are aligned in the same direction. If they are not aligned in the same direction, it will break. And what I'm saying here is that in 1D, for any temperature, they will break. I can give you a more maybe simple example. At Christmas, or in India, we have this festival called Diwali. What we do in these festivals is to put up these lights outside our house. You know what I'm talking about, right? These electrical lights, which are all on or off at the same time. So this is like a circuit where if one of the lights fail, the whole thing fails. And you must have experienced this, right? One little bulb will fuse in the whole lights. It used to be very frustrating as a kid. And then the whole thing failed. And you have to go and figure out which bulb failed. Because when you observe it, it looks like none of the bulb is working. Now you have to go and figure out which bulb failed. So what it is showing here is that at any temperature, something will fail and you will have complete chaos. The magnetization will go to 0. So in 1D, the average magnetization is going to look like this in 1D. Tc is equal to 0. In 2D, however, there is a finite.
Your screen froze.
Oh, my screen froze.
Not updating again.
Oh, that's awful. I should go and short Zoom stock. Share screen. I was not writing anything profound, so okay. Good. So what I was saying is that in 1D, the red line applies, the critical temperature is 0. In 2D, the blue line applies, that is the critical temperature at which you can still have magnetization. And in 3D, apparently, this critical temperature becomes even higher. And in general, as you increase the dimensionality, the critical temperature becomes higher and higher and higher. This is quite profound. This has strong repercussions in information theory. This is telling you that in 1 dimensions, any change in the system will percolate to the other end of the system. Even if you have a slightest driving force for the information to percolate, again, think of Facebook. If everyone at Facebook, I'm not going to say political things today because I'm so pissed, so I won't use Facebook as an example. But in 1D, information will percolate from, and everything will just affect each other and stop. In 2D, on the other hand, you can have pockets that look like each other and they can persist. In higher dimensions, the tendency for these pockets to persist becomes even easier. This is what we are going to look at from a more physical perspective now as to why this is the case. We are going to use an argument which I like quite a lot. It's a very physical argument. Its name is, if I can get the spelling right, I'm probably going to get the spelling wrong, but it's something like Pearl's droplet argument. If you go and Google Pearl's droplet argument Ising model, you will get the right spelling and you can look at it. We will first look at it from a Pearl's droplet argument. We are then going to look at these critical temperatures using something called a mean field theory. And then we will look at the same critical temperatures from renormalization group theory, which is also called, abbreviated as RG theory. So the Pearl's droplet argument will show you quite intuitively as to why in 1D there is no phase transition, that the critical temperature is 0. And in 2D, you can have a phase transition at a non-zero critical temperature. Mean field theory does that in a more mathematical way. It's quite nice. There is a problem with mean field theory. It overcompensates it. You will get critical temperature even in 1 dimension, which is actually wrong. But in higher dimensions, mean field theory tends to do well. Renormalization group theory is a beautiful idea. We won't go into all of the details. I will give you some additional problems from Chandler where you can go and look at them to get a flavor of what happens in higher dimension. But renormalization group theory gets the critical temperature quite right. So let's think about Pearl's droplet argument. So we will start with Pearl's droplet. And what we are going to do is to look at a 1D chain of states. So what's the, and all this we are doing in no external magnetic field, okay? We are not worried about external magnetic field right now. We will introduce it in the mean field theory thing, but there also we will take the limit where it goes to 0. But for now, there is no external magnetic field. So how will the ground state look like? Oh, by the way, I wanted to comment on the homework. Most of you did very well. I'm happy to see that. There was one problem in which a large number of you got it wrong. It was very tempting to divide by 2 factorial. But remember our whole thing about how do we get classical distribution functions from both Einstein or Fermi-Dirac, where we use Stirling's formula in reverse. We could not have done that if n was not large. So if n becomes large, that approximation becomes progressively more correct. But for small n, that is not a correct approximation. In fact, for small n, B should be the same as D, which some of you realized and got that right. I think half of you got that right, which is very good. So the ground state for this 1D chain of states could be all of them pointing up or all of them pointing down, right? And we are not going to worry about what happens on the boundary. We are not in a flat Earth scenario. Everything is periodic. Earth is best example of periodic scenario. Everything comes back. So there is a chain or it's infinite number of spins, whatever you want to think about. So what is the energy? So let's say we have n such spins. And let's say the energy model for the spins is given as minus j, SIFJ. And let's say that we have only first neighbor interactions. We are not going to think about higher neighbor interactions. If you have only first neighbor interactions and all of the spins are pointing up, what will be the energy of the system? Anyone wants to help me? Thomas, I haven't asked you a question ever, so you should tell me. So all SIFJ are equal to +1 or -1. Think through it carefully.
This is for just one neighbor interacting with the other.
But tell me about one neighbor. What will be the energy of one neighbor? That's a good start. Exactly. So what is the energy of one neighbor? Let's ignore this sigma. Let's just think about one neighbor. What will that be? Minus j SIFJ. So that's equal to how much? If Si and Fj both were +1, then this would be equal to how much?
That would be equal to -1 or negative j.
Negative j. And if Si, Fj were both -1, then how much would this be?
That would still be negative j.
Negative j, exactly. So this is energy per pair. Now the question is, how many pairs do we have, right? That's the whole thing. And here we are going to be a bit sloppy. If you had n spins, not sloppy, if you had n spins with periodic boundary condition, then number 1 and 2 make first pair, number 2 and 3 make a second pair, number 3 and 4 make a third pair. So fourth one gives to a third pair, fifth one gives to a fourth pair, nth one gives to a n-1th pair. But then we are thinking of periodic boundary. So we have n pairs, right? Or something like n-1 pair, even if you did not have periodic boundary. So, but something which is n and n-1 are very close, right? For n tends to infinity, there is not a huge difference. So E is equal to minus nj, correct? Thanks, Thomas. Okay, good. So in the ground state, this is the energy. Now let's think about flipping some of the spins, introducing a bit of disorder in the system, right? How do we do that? So we have some spins pointing up, up, up. And let's say we put a spin as down. I will use a different color. Down, down, down. Let's just start with only one spin, and let me do it on the next page. So we just showed that E ground state, or Thomas just showed that E ground state is equal to minus nj. Now we are talking about the energy of an excited state, where the excited state, let's consider, for example, is we just introduced one spin to be opposite of everything else. So what is the energy of this configuration? Anyone wants to help me with this?
n-2j.
It's actually, it's a bit subtle. Why? Because this, so first of all, which pairs changed? These are the two pairs that changed, right? Everything else was unaffected. So let me use color red for it. This pair changed its energy. This pair changed its energy. This pair was same. This pair is same. This pair is same. This pair is same. So this pair over here, what was its energy earlier? Its energy was -1. Its energy was +1, right? Now it changed its energy to -1. So the delta E for this pair on the left was 2. Similarly, the delta E for this pair was 2. So the difference is 4J. It's not 2J. It's a subtle point, but it's 4J. But this is a beautiful argument, because what's nice about this is, now let's not just consider one spin that has flipped. Let's consider that the domain that has flipped is much bigger than 1. Let's say it is, I don't know, 5 spins. The same exact argument applies now. These two have the same interaction energy. These two have the same interaction energy. These two have the same interaction energy. Nothing changed. Why? Because you brought it from both up to both minus, but the energy still stays +1. Nothing changed. So the change in energy happened only here and here. So even in this case, E excited. So this was one spin flipped, and this is many spins flipped. So the energy here is still -n+4j. That's kind of very nice. I like it a lot. It doesn't matter to how much size did you change. So there is an energy cost, right? If you look at it, the ground state had -nj energy, while the excited state has -nj plus 4j. So in order to flip the spin, you have an energy cost, which is 4j, right? So this comes from, let's number our equations, ground state 1, excited state 2, by looking at 2 minus 1. The energy cost is 4j. So this is one way of looking at it. This is telling you that at any temperature, there is a cost of flipping the system. But this might give you hope that maybe there is a critical temperature, right? Because there will be some temperature at which, so what does this mean? This means that if there was only energy which was playing a role, then the probability of observing such a spin such a flip. So let me write it down. If only thing that mattered was energy cost, then probability of observing a flipped domain would be e to the power minus 4j over kBt, right? Boltzmann probability. So you could think here that maybe if I make the temperature small enough, and if the J is large enough, then there will be some temperature at which things don't flip, right? So if it was just this, it kind of makes you feel like maybe my average magnetization could look something like this. I broke my iPad screen by watching too much Netflix, I think, during this quarantine. It would look something like this. There would be some temperature. It would be a small valley. Does everyone see that? Because this is an exponential thing, right? It could look like an exponential curve, something like that. You could observe a block domain, and things would be chaotic. But we missed something. We have so far just considered the energy cost. There is something else that we need to consider. Anyone realizes what is that? What is it that we forgot? The bad brother of energy, which is entropy. There is an energy cost, but there is an entropy gain. Because a system which is like in the ground state can always exist in any one conformation, right? Now, if you have a system with 2 spins flipped, then this system could exist like this, or it could exist like this, or it could exist like this. Many, many more. Many ways to have excited state, one or maybe two ways to have ground state, right? All of them up or all of them down. So there is a entropy gain that we get because what is entropy in the end in a macroeconomical ensemble is the number of ways of arranging the system. The number of ways of arranging the system is many more here. So now we can think about the free energy cost to create a block of flipped spins. What would that be? So we are thinking about delta A. Delta A would be equal to 4J, which is the energy cost, minus T times change, KT times change in entropy, right? How do we talk about change in entropy? How do we think of that? So the question is, how many ways in which, how many ways are there in which we can arrange this block of spins? So if you have n spins in total and n tends to infinity, then this block could start from the first spin or from the second spin or from the fifth spin or from the third spin or from the fourth spin. So this thing is, it could start in n different ways. N different ways of arranging the ES. If you were not thinking of 2 spins, you were thinking of block of 3 spins, then it would be n minus 3 different ways, right? But first of all, we have periodic boundary conditions, and secondly, we are thinking of n very, very large, so we are not worried about that. So this thing is 4J minus KT S is equal to K log W. So why do I have K here? So this is going to be K log N, because the number of ways of arranging the system is proportional to N. So this is our free energy cost. And if you monitor, and what are we interested in? We are interested in thermodynamic limit. Thermodynamic limit means N tends to infinity. So as N tends to infinity, delta A tends to 0 for any T. That's our argument. Is that clear? As N tends to infinity, this second term absolutely wins. The entropy gain wins by such a margin that this puny energy term cannot capture it. It cannot keep up with it because energy term is, and that's the point here, the energy term does not depend on N. The energy term is not extensive while the entropy term increases with log of N. So if we plot the delta A versus temperature for this system, it's going to look like this. I don't know how quickly it will drop down, but it will start at 0 for any non-zero temperature. The free energy cost to create disorder in our beautiful 1D ordered system is vanishingly low as N tends to infinity. So in the thermodynamic limit, a 1D system cannot sustain order. It will become disordered. So that's Pearl's droplet argument in 1D. Now let's try to move this thing to 2D. So here, this, when you go back and see this, this might look like I drew 2D spins, but it's not. This is 1D, the thing to keep in mind. So any questions about this? Okay, so let's talk about 2D. Don't worry, we won't go to 3D. I will send you a note about how this analysis can be carried out in general dimensions. Oh, I said I'm not going to 2D. Why did I not going to 3D? So what happens in 2D? So 2D, our ground state will again look like all spins up, right? Or all spins down. Let's start with all spins up. we are soon going to revisit this question of degeneracy between all spins up and all spins down, and what does it really mean. That's also interesting. We'll revisit that in a bit. So let's create a bit of disorder here. Let's make this spin point down, and maybe this spin also point down, and something like this, and the others still pointing up. So now we have created a block of spins which looks like this. So we have again created a boundary which, and it's the boundary that really matters. It's the wall that matters, right? That's where the energy comes, the energy cost comes, because deep in the bulk over here, the energy is the same as these two spins here. So the energy cost is coming only from the wall. Here you have something which is already quite different from what happened in 1D. In 1D, the cost of creating the wall was 4J, period, right? Because the wall cannot go across the system. It does not depend on how big was the domain that you flipped. Your domain could have been 2 spins, 1 spin, or 4 spins, or 5 spins. The cost was always 4J. Here, it's not the same. Here, the cost, if your domain has n members, so this one is 1 pair, this one is a 2nd pair, this one is a 3rd pair, this one is a 4th pair. And in 2D, you have to be careful about how you define your nearest neighbors. We are not going to be extra careful. We are just going to go with the flow in this case, because we are going to do this mathematically anyway later. So here you can see that the delta E, if your wall had L pairs that got broken, okay, what would be the delta E in this case? Any help? I'm stuck, I need help.
Two L.
Yeah, Shokang is correct. 2L or 2LJ? 2LJ, right? 2LJ. So you can already see a difference. This is not 4J, this is 2LJ. So you can already see that the energy cost has maybe something that's going to step in and create a competition. What is more interesting here, so again, we are going to write down delta A is equal to delta E minus T delta S is equal to 2LJ minus KT ln W. So what we need to find now is W is the number of ways of creating the wall. This is an interesting, go ahead.
Excuse me. But there are some of the red ones that are down. They're connected to 2 ups, right? Like if you look at the second one that you draw, it's connected to the up and to the right one.
I will
So
count
they
them
are.
as 2. I will count them as 2. It's the number of pairs will go up by 1.
Oh, so this would be like in the L, you're counting this as 2?
Yeah, so the way I'm deriving it, it's agnostic to how you define the interaction. It could be
Okay.
an interaction only, it could be side, but it doesn't matter. If it's an interaction that you consider, then L, it will be included in L. If
Okay.
it won't be included. It could be some other lattice also. So it's quite generic. Okay? Yeah, good question though. So now we have to think of the number of ways of creating the wall. And this is a bit interesting. Here I'm going to give you a bound on the answer. I won't give you a true answer because it's a bit complicated. I will give you a bound on the answer. So let's say, and it would be nice to use some different color. Let's be gray. Let's say green. So let's say I start over here with my green color. I can move up, down, left, or right, right? I can move in 4 different ways. For L, so if my wall has L different parts, L different pairs, for the first one, I can move in up, down, left, or right. For the second one, when I come over here, I cannot really move back, right? I can move again up, down, right, but I move left, then my wall will be annihilated, right? I would have come back. It's like making the wall and coming and removing it. I cannot do that. So I have to move in some other direction. So what you can see here is that W is going to be less than 4 multiplied by 4 multiplied by 4 L times. So W is going to be less than 4 to the power L, right? Because if at every point you allow the wall to move in any of the 4 directions, you will just come back and cross it, okay? At the same time, you would expect that W is going to be more than 2 to the power L. Why? Because if it was just 2 to the power L, that would mean that your wall looks like here you have 4, then you come over here and you can move up, down, or right. You can already see you have more than 2 ways of moving, right? So if you only allowed for movement in 2 directions at every point, your walls would be very limited. Let me draw it over here. So if you only allowed movement in 2 directions, your wall would probably look, once you got over here, now you can move up or down. So you can go here or you can go down here. You are removing this movement, for example. So it's definitely going to be more than 2 to the power L. So there are ways of calculating this exactly. But what we are going to say is that, so 2 to the power L is going to be smaller than W, and it's going to be smaller than 4 to the power L. So we are not mathematicians. Well, Luke is a mathematician, but we are not mathematicians, so we are not going to care about Luke. We are just going to say, well, let's set it as approximately 3 to the power L. Why? Because it's kind of in the middle between 2 to the power L and 3 to the power L. It's an approximation, right? But it's well bounded. We know it's between what we had. So now we can calculate delta A as delta E minus T delta S. Then how much was delta E? That was 2LJ. And this is minus T. Oh, someone sent me a message or something. Who sent me a chat message? I don't know. Turash says, why not more than 3 to the power L? It could be more than 3 to the power L. What I'm saying is, I could even set it as 2 to the power L. I could even set it as 4 to the power L. The point is that it is in that regime, okay? It is some number. It is some k to the power L where I know k is going to be somewhere in 2 to 4. Do you buy that, Turash?
Yeah.
Good. That's the argument. You will see that this leads to a critical temperature. The exact value of the critical temperature will depend on whether you get this number right or wrong. That's a pretty good bound. You know, we are saying between 2 to 4. It's not a horrible bound. I mean, come on, we are doing statistical physics. 2 is quite, it's not too bad. It's in that domain somewhere. So we will say, let's say 3 to the power L, or in order, or 2 to the power L. It doesn't matter. It's some number between 2 to 4. I'm just writing it as 3 to the power L. So what is delta S? Delta S is ln W. So this is K, ln, and K is bad notation because Boltzmann constant came up. So let's call it J to the power L, where J is that part. So, but we are not going to worry about that. We are just going to use 3 to the power L over here. So what is this? This is 2Lj minus LKT ln 3 is equal to L 2J minus KT ln 3. And this could have, here instead of 3, you could have put your value of J. It doesn't matter what it is. The fact is you will have something that looks like this. And in the end, ln 3 and ln 4 are not all that different from each other, right? They're kind of similar. It's not that much of a difference. What does this tell us? Now, if you plot this delta A versus temperature, it's not going to look the same as what we had for 1D. In 1D, it looked like something like this. It was always negative. Here, on the other hand, it's going to be positive because if KT ln 3 is less than 2J, or T is less than 2J by K ln 3, then delta A would be positive, and you have a cost for creating the boundary. So this is what we call as our critical temperature, 2J by K ln 3. And here, delta A versus temperature is going to look something like this. Delta A more than 0 if T less than Tc. Delta A less than 0 if T more than Tc. So this is why I was not too fussed over this value of 3 to the power L, 2 to the power L, 4 to the power L, because it's ln3 and ln4 are not phenomenally different. But you get a critical temperature. That's the most interesting thing. And what was Onsager's exact value? Let me look that up. Onsager, let me look it up on here also so you can see. I'm browsing. Where did Zoom go? Onsager. Oh, since I am on Google, I want to show you something interesting. I think I am, if I remember right. So Onsager was buried in Yale University. And this is his grave. I think it's quite an interesting grave inscription. This is the full story. So Kirkwood and Onsager had lots of competition, and they were two statistical physicists. So Kirkwood died first, as you can see, in 1959, and they buried him in Yale, and he was quite proud, or his family was very proud of what he had done. So he had a full description on his tombstone of where he got his degree. You can see his BS degree is written over there and everything. And then Onsager, when he buried, he insisted that he be buried next to Kirkwood, and he insisted on his tombstone as a kind of a joke against Kirkwood's tombstone, saying that he won the Nobel Prize or something. So this is a story about that competition, but I got distracted. Let's go back to Onsager. Critical temperature and see how good did we do in our calculation. 2 by ln of 1 plus root 2. We got really, really close. Think of this, right? Onsager's exact answer in the bottom has log of 1 plus root 2, while we are talking about log 2. So let me go back to this. So Onsager's Nobel Prize answer says it is 2J by K ln 1 plus root 2. Anyone remembers the value of root 2? It's 1.414. So this is 2J by K ln 2.414. That's pretty good with such a heuristic argument that we got to something. I mean, we should get half a Nobel Prize for this, right? No, we won't. His answer is exact. It is exact to any decimal value that you want. But still, it's amazing that using an intuitive picture of thinking about how many ways can we create a wall, what is the energy cost of creating a wall, what is the entropy gain in creating a wall, we can get a pretty good answer. In fact, you might argue that maybe, so as you can see, the true answer is probably between 2 to 3 for a square lattice. And you can go and think about it as to why that is the case. So this Pearl's droplet argument can be applied in 3D also. And you can kind of see why it would lead to even higher critical temperature in 3D, because the cost of the wall would become even more, right? So there can be even more temperature until which so this over here is 2D, and in 3D, it would start to look something like this. The wall, the cost to create the wall stays positive for an even higher temperature, is because the energy term starts to dominate even more and more. We are not going to go into 3D. We are going to look into Ising model now from the perspective of mean field theory, which is a beautiful idea, and that will do all of this in a more mathematical setting. And we will calculate all of this in a mathematical setting and see how it looks like. I want to mention a couple of interesting applications of Ising model before we do that. So, this is page 11. So, many things can be mapped onto an Ising model. So for those of you who have done any material science or physical chemistry, you would remember things such as face-centered cubic crystal, right? And hexagonal close-packed crystal. So a face-centered cubic crystal is actually given by layers that look like ABC, 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 while a hexagonal close-packed crystal is given by AB, AB, AB. Some of you might remember what this ABC, ABC is. So it's all about arranging spheres. So in face-centered cubic, you have in any one layer, you have these spheres that are arranged as follows, right? You have a hexagonal packing. So this is called the layer A. The next layer is arranged on top of this, and it can look like this. It will again be hexagonal, and you can have some arrangement. The third layer can have, so this is now called a layer B, and the third layer can be the same as the layer below it, or it can be a further rotation. So the point being that this 3D crystalline symmetry can be mapped into a 1D arrangement of close packed layers. These are called close packed layers. And you can map this into an Ising model. How do you map this into an Ising model? You say that if between two layers, A is going to B, let's call it as a plus spin. If B is going to C, also call it as a plus spin. If C is going to A, also call it as a plus spin. So if you have this type of arrangement, A to B, or A to B, or B to C, or C to A, let's call it as a plus, which is like a clockwise arrangement. Or if you have an arrangement where B is going to A, or actually, let's write it down this way. So in packing of crystals, you can never have two layers repeating. A cannot be repeated by A. That's why we can arrange it this way. So, but if A cannot be repeated by A, what can be the next layer? It can be C. Similarly for B, what can be the next layer? If it's not C, it has to be A. And for C, if it cannot be A, it can be B. So if you have this type of arrangement, let's call it a minus spin. So now you can see that this FCC crystal is actually similar to plus, 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 all spins pointing up. So you have A to B, B to C, C to A. It's always in this category. In the HCP, you have A to B, which is plus, but then B to A, which is minus. A to B, which is plus, B to A, which is minus. Black, black, black. So in material science, sometimes what happens, you have arrangements that look like ABC, 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 and then suddenly it switches to AB, AB, AB. So the crystal over here is face-centered cubic. The crystal over here is a hexagonal close-packed crystal. And this thing over here is a fault. Does anyone know what is this fault called? If you have taken any solid-state physics or material science, you should remember the name. It's called a stacking fault. So, and these things are enormously important when you're trying to model the property of a material. So you can consider stacking faults in terms of Ising models. You can see how spins are arranged and how they change. I introduced this example because when I was doing my undergraduate degree, I actually published a couple of papers where I took stacking faults and modeled them into Ising model. Then I calculated the phase diagram, and then I calculate the X-ray diffraction profile of that. So you can do a lot of fun with this. People also, what other examples can I give you for Ising model? People use it to model liquid and gas or crystals. Let's say you have a bunch of liquid atoms, and suddenly you start to form a crystal over here. So this is liquid atoms, and you suddenly start to form a crystal. If an atom is still in liquid, you call its spin as -1. And if an atom is in crystal, you call its spin as +1. And through this, you can model the nucleation process. As the nucleus becomes bigger and bigger, the +1 region will become bigger and bigger and bigger. And it will start to look like this. So you can imagine that as you study the magnetic moment of this thing, not the modulus, but the magnetic moment of this thing as crystallization is happening, when the full thing is negative, it's going to look like -1, and as crystallization happens, it's going to look like +1, and there you have nucleation. So you can map the nucleation problem into an Ising model problem. There are lots and lots of papers where people model Alzheimer's disease with Ising model in terms of whether a cell is in a certain state or not in a certain state. Ben mentioned last time there are multiple papers on bioRxiv trying to model whether you have coronavirus or not as an Ising model. If you have a coronavirus, we call you as -1. If you don't have coronavirus, we call you as +1. And then you can think about how the pandemic spreads by looking at the J factor, right? If J was like in the pop quiz, that's not clearly true for coronavirus, right? Because if you are +1, then you want your neighbor also to have coronavirus. You don't want it, but that's what will happen, right? And suddenly you will have -1. And yeah, so there are lots and lots of applications. It's a powerful thing. I encourage you to go and look up the Wikipedia article on Ising model, or just do a Google search and you will see where it's applicable. You can also think of your own research as to how you could use it. Next class, we will think about mean field theory. So this Pearl's droplet argument is not given in Chandler's. I think we should have given it because it's quite nice. Chandler talks about mean field, and that's what we are going to do next. So I will stop a bit early today, and I will give maybe one more homework after this. This week there won't be any homework because I want you to take time and go through the papers. I will be very lenient in giving you grades in the exams. Just make an honest effort. Okay, if you don't make an honest effort, I will still give you a good grade, but I will bombard you with emails and ask you, why did you not make an honest effort? And we'll try to understand why you did not make it. I will just be, instead of giving you bad grades, I will try to become more obnoxious. This is what I can do. If you want to submit reports on more than one papers, that's also totally fine. If you want, like one student mentioned to me, they like 2 papers, well, do that. It doesn't matter. I will be if you submit reports on 2 papers, I will definitely give you full grades. There is no doubt about it. You will have to, however, select one paper for the presentation. You can submit reports on more than one. You can also submit presentations on more than one. But when you make the 4-minute presentation, you will be doing it on only one paper. Otherwise, you will run out of time. Okay, so see you next class.